Okay, so today's lecture we start learning the first steps into analyzing slightly different structure, which is beams and columns. Or today's lecture mainly will be focusing on beams. And the step number one to analyze beams, we have to calculate the internal forces and actions into these beams. So I did say forces or actions in the beam because mainly what we looked at during the truss, if you remember, or what we had, one type of forces, axial forces. We looked at tension and compression forces in trusses. That's only one type of force will be developed inside a truss, whereas for a beam, we'll have slightly different range of actions in there. We will have the shear forces, the axial forces, and the bending moments. So this is the main difference between trusses and beams, guys. Beam will work all together, all the particles inside the beam. Doesn't matter what type of particles, timber, steel, concrete, or composite concrete and steel, which is reinforced concrete. Those particles will work together inside the beam by providing tension and compression within the cross-section of the beam. So we've got tension zone and compression zone within the beam, and that will create the moments, as well as we've got the shear forces. Shear forces are all the forces perpendicular to the beam, or not perpendicular only, but with an angle, has a angle applied to the beam, so it's not perpendicular to the cross section, put it that way. If it's not normal forces or axial forces to the cross section, that means they are shear forces. They have a value of a shear force. So this is concept one. We have to keep that in mind. In trusses, all what we had are just axial forces. These forces are always normal to the cross section, working in tension and compression, whereas for beams we have shear forces as well as the normal forces. So a beam may have, I'll give you an example, a beam designed to support the roof will have the weight of the roof in this form, which will be a shear force applied on the beam. This shear force at a certain distance will create a moment inside the beam. Also, this beam supporting the roof is resisting the wind from the side here. We've got the wind applied to the roof, and that's trying to compress the beam. So we'll have some axial forces running within the beam. Okay? Without worrying too much about it, all what we need to know, a beam structure will carry these three types of actions: axial forces, shear forces, and bending moments. And this will give us our three equations, as usual, to solve problems or to solve the design scenario. Now, to analyze a beam, we'll follow the same in theory. We'll start with the theoretical component. We'll follow the same approach, what we've done for the method of sections for trusses. We'll apply the method of sections for beams. And the method of sections for beams, simply all what we need to do is just we take a section. We can take a section at any point. If I need to know, in other words, let's go back to trusses. If I needed to know the forces in these members, I took a section at these members. If I need to know the forces at these members here, I can't take a section here. I have to take it here. Similarly, if I need to know the bending moment value, bending moment, that means we are referring to M, the bending moment or the shear force or the axial forces at one location, at this location here at point B, I have to take a section at that point. Now, if we take a section at that point, if you remember what we learned from trusses too, the first thing before we'll be able to take a section, to be able to work with that section, we can't keep supports. We have to change supports to reaction forces. We have, in other words, to draw the free body diagram. So the same approach we'll do for beams. Instead of having a support here, and anyone will be able to tell me what type of support we've got here? First of all, what type of supports we have usually for beams?
This is a cantilever.
This is a cantilever beam, correct? But what kind of support do I have to provide or to be able to create a cantilever beam?
A fixed support.
Perfect. So we agreed we have mainly 3 different types of supports. I'm just trying as much as I can because I wasn't with you guys for the first part of this subject, to make sure that we are clear on these fundamental concepts. We have 3 main types of supports for a beam. We have the roller support, will provide only vertical reaction. When I'm saying vertical, that means for horizontal beam, or in other words, will provide one reaction which is perpendicular to the support face. We've got the pin support, will provide 2 components of reaction, horizontal and vertical support. And we've got the fixed support, will provide 3 components for the reaction: vertical, horizontal support, and moment support will stop rotation. Okay, let me just show you, make sure we're clear on this. Picture 6, I think, if I'm not wrong. Yep. Okay, so these are the main 3 supports that we've got, guys, and that's all I'm saying. Depends on what direction the roller is, the reaction force will be perpendicular to the support face always. So if I have the roller supported on an angle, the reaction force will be always perpendicular to that. And these some examples of roller supports in actual application. And the pin support will provide vertical and horizontal support, but doesn't provide rotation restraint. So it will allow rotation. There is no moment support, or what will provide vertical and horizontal force support. Example, guys, this is a pin support here, supporting the bridge, the harbor bridge. So it will allow rotation, but doesn't allow vertical or horizontal movement. Similarly, we've got, this is many examples of pin supports. This item, this member here, and those are the supports we usually use for trusses. Look, this is a kind of arrangement for one of the trusses arrangements, okay? This member here can rotate, but it can't move vertically or horizontally. That's the definition of pin support. Fixed support, that means it doesn't even allow, yes, it doesn't allow moving vertically or horizontally. At the same time, look at it, it's a very rigid support. Mainly, we achieve moment support by providing the top and bottom flange of the beam. We'll talk about this more in next year for the structure analysis. How do we estimate, how do we understand to make the decision on, is this a fixed support or a pin support? So if I have something fixing the beam, if we're talking about beams, for example, and fixing the top and bottom flanges with a rigid connection there, that will be a fixed support. Doesn't even allow rotation. Can you think of this beam trying to rotate here? It can't. Similarly, for another arrangement, if I have a column encased into the concrete, if the column base is encased within the concrete, that means this is a fixed support, doesn't allow rotation. So this is the comparison between the 2 supports, reactions, just to make sure this is a quick review. You guys familiar with those, okay? So this is some examples here, we don't need that. Going back to our lecture, So the type of support here we have is a fixed support, because that's the only type of support we provide a cantilever beam. Okay, so going back, if we need to analyze a beam, we agree to take a section at that point. Before we do that, we have to change our beam to a free body diagram. We can't keep supports like this. We have to make these supports as, we have to represent these supports with their reaction forces. Therefore, this is a fixed support. We'll provide 3 different reactions. We'll put the reactions in there. And if we take the cut at the point B, we agreed that we have to replace other half with the internal forces. That's what we've done for method of sections, for trusses. Now, the only difference that when we take the cut at a beam, it's not only just normal forces or axial forces, both are the same, normal, that means normal to the cross section, perpendicular to the cross section. So it's not only axial forces, but also we have shear forces and moments, because beams are not 2 force members. Beams, they have shear force, they have bending moment, and they have axial forces, tension and compression. Are we good with the concept in general, guys?
Aaron, just I have a question.
Yeah,
I'm not clear with shearing forces. Could you please give more details or examples, please?
yeah, of course. We will, that's mainly our work today, to start looking at shear forces. But okay, that's fair question. Let's think about it this way. All right. Who asked the question, please? Sorry, I didn't see the. I can't recognize.
This is Hannah. This is Hannah. Aaron.
Okay.
Yes,
Thanks.
that's
Hannah.
nice.
Yeah. Okay. So, Hannah, think about this force here, force B1. Okay. We are assuming, without worrying now about cutting a section and all of that. Don't worry about all of this. We are always assuming if I have a force B1 here, ignoring B2. If I have a force B1 here, actually, let's take this to our whiteboard. Okay, ignoring this force here, just so we can simplify the case, we understand what's going on. So if I have this beam here, this force B1 is applied at this point here. How would you, we all know and we agreed that the reaction here would be, I've got a horizontal force. We've got a horizontal force there, reaction, vertical reaction, and this is the force applied this way. We try to bend, and then we've got a moment applied that way to react. Okay, so this is MA, and this is F or R A Y, RAX equals to 0. I'll ignore RAX because there's no forces currently horizontally. Okay, these are the 2 main reactions we've got there. The question is, we all know that RAY, do you agree, Hannah, that RAY should equals to P, simply, because that's from sigma Fy equals to 0. This beam should be balanced in the vertical direction. That will make the reaction here equals to the force B1. That's B1. All good? The question is, how this force getting transferred to here, or how is the reaction stopping this force from moving the beam down? So what happens there? If you try to think of these particles here inside the beam, the steel particles here, there's lots of these particles next to each other. These particles, think about them, they're connected together with some electrical and electronic and magnetic fields, okay? These fields and these joints between the particles, they work as springs, as if I have, for example, if I really exaggerate and enlarge this area or any area in the beam, there'll be small particles like this next to each other. and these particles together connected with springs, assume. All of them. Okay? So you added the force here. And the reaction is happening, if I extend all the way, is somewhere there. What happens there? When you added this force, simply you are forcing these particles here to move down. You're just making these forces, these particles trying to move down. But we agree, these are springs here. They will stretch. They will stretch for a little bit, going that way. But then they will try to balance it and push it up. And to be able to push it up, these particles will go down. And the same thing continuing all the way there. These particles will go back up, like that. And these particles now will move down. All the way until they get to this point here, and they start affecting, this is the support. Let's draw the particles of the support in a different color and different size, for example, until they get to here. That's where these particles here of the support will provide this reaction and will bring back these particles up. Obviously, this is very theoretical concept. It's not the actual scenario there, but just so you understand, it's just all particles of steel. Think of the beam here as a group of small particles connected together with that electromagnetic field between them. If you try to, how would the axial force work? If I try to push on these particles here, that will compress this spring here. Will make it compressed, and that will force it to make a reaction, push those back, and this will move that way until the wave will move along the entire beam, and the force starting from here will reach that end there. So it's just, don't look at it as a steel beam and just all solid member. There are all these particles working together, and this is the transfer of these forces together. So when we say shear forces, just to answer your question, Hannah, are the forces are trying, look at these particles here. I've got this column of particles, and I've got that. When we talk about shear forces, the word shear, that means you cut. You're trying to cut something, like scissors. Think about have you ever thought about how the scissors cut the paper? The scissors would be cut the paper, or any machine will be able to cut the steel, for example. It's by adding two large forces very close to each other. Very close to each other, at very close distance. That's how scissors. If the paper here between them, these are the two blades of the scissors, will cut the paper there. That's the word shear. So these forces, look at it. This force here is trying to move these particles down, and these particles are reacting up. That's what creating the shear forces. When we have these, the direction of the force perpendicular to the entire beam, like what we had these forces perpendicular to the paper, that will create the shear action. We try to shear the paper, or these forces are trying to shear, cut the beam here. Realistically, this is not going to happen unless you apply two large forces at very close distance. But in theory, that's why we call them, they are shear type forces. I'll give you an example of these type of forces and the transition between them. Where is that? I think, just 1 second, please. Okay, so to understand what we're saying here about the movement of these particles of steel and these spring effect between them, look at this example here. This, the top example is the transverse direction or the shear forces. Look, when the wave or the force is applied here, the reaction from the member, we're trying to move that force along the entire member until we get to the reaction. This example at the bottom here is showing you the axial forces, how the axial force is trying to compress. If I'm adding a force to compress the spring, how the springs between the particles will move that axial force along all the particles. So just to give you, that's when we're adding the force, and that's how the spring effect between all the members moving forward. For the shear force, that's where we apply the force, and the particles will react to that and just moving this shear force. So the shear force always perpendicular to the member. If this is the beam, the force is always perpendicular to that beam. If we have this force very large and the reaction here very large in the opposite direction, that will cut the beam at that point there. So if I take you back to what you learned about the yielding point, the ultimate failure, all of these theoretical concepts that you guys learned, it's all about the capacity of these joints. That's what creates the strength of materials for different materials, guys. So if I'm using a high strength steel, that means the springs between these particles is very strong. Because the yielding point, when we say the word of yielding stress or yielding strength of material, it's the point where these, if I pull this spring too much, what will happen? To a certain stage, will stay as spring, will go back to normal. But then if I go past that elastic point, that will create a permanent damage or permanent deformation. I wouldn't call it damage yet. Permanent deformation. That's the yielding point. It's the point the force you applied was stronger than the material. You made the material yield. You won, or the force won, the material lost. That's the yielding point. That means these springs here, they stretch too much, so they can't go back to normal. The point where we talk about the ultimate failure or ultimate rupture, it depends now what direction we are applying this force. Imagine I'm applying very high tensile strength here, tensile force here, tension force. I'm trying to pull the ice a lot. First of all, these springs will stretch, and that's the yielding point. And then if I continue past that point all the way, I reach a point that where these springs will rupture. And that's what we call ultimate failure points. Now, if the force wasn't axial, if it was this direction, perpendicular to the member, the same thing. If we reach a point here that's too strong, these springs will stretch too much, and this may shift these particles. This will cut from here, and just this particle here will find itself closer to that point rather to that point. So we'll shift a little bit. And that's what will cause a slight deformation as we go further until all the joints between the particles will cut and will be sheared. and that's will be the ultimate failure point. So just to go back and answer simply your question, shear force is the force applied perpendicular to the beam. It's this type of wave. This type of wave, perpendicular to the beam. The axial forces are the forces will be within the beam, in that direction. Did that make sense?
Yes, Aaron. Thank you so much. So clear, mate.
All right, good. Okay, so we'll go back. This is done for today. We'll go back to our lecture. So talking about now, bending moment is slightly different than both of them, guys. Always think of a bending moment is a combined action. We call it combined stress, if you remember, from the stresses that we looked at. It's a combined action between tension and compression within the member. We'll talk about bending more and more down the track. But for the going back here, if we are going to cut the beam, if we, based on the method of sections, if we decide to evaluate the actions or the actions, the forces and the bending moment within a beam at any point, all what we have to do, cut that beam at that point. Obviously, after we draw the free body diagram of that beam, and then we go back to our agreement of which part do you want to choose, the left part or the right part. Doesn't matter, both of them will work. Okay, if you calculate your reactions, that means you take this part here, because this is a cantilever. In this particular scenario, the same as a cantilever truss, there's a chance you don't need to calculate your reactions. You could have just made the cut and took this part here, this half. Very similar to the example we looked at. The main difference we've got so far, guys, if you noticed, rather than just adding one force there in tension, I've added three shear force, normal axial forces, and bending moments, because these actions all will be in the beam. Now the question is, as we agreed in trusses, that always let's agree on when we assume the forces, we assume them they are in tension, and that's what we've done here. If you look at it, if I take this half, we assume the internal forces are in tension, and we will see if that's correct, we'll keep it. If not correct, we'll change it to compression. But what about shear forces and bending moment? What is the sign convention we're going to use? By the way, guys, just please keep an eye, or anyone can answer me why I have this force in compression, not in tension. Did we agree that when we make the cut, we made the internal forces always in tension? Why do I have the force here in compression, not in tension?
Is the reaction to the P2 force?
Thank you. So we are talking about assuming these forces in tension. That's when we take the cut. These are internal forces due to the cut of the beam. These are completely different. These are reactions. So dice, we usually apply them based on the reaction, if you remember. Not all the time we assume dice in the positive direction, negative direction, anything like that. Okay, we'll always just look at the reaction and we calculate based on the reaction, we apply these forces. All good? But when we take the cut, the first thing that we already know, axial forces will be in tension, assumed. And then we will analyze from there, we'll see. But what about shear forces? The rule, the sign convention for shear forces. So we agreed, if I take this side of the beam as a cut, the shear force will, the axial force will be in tension. If I take that side, the axial force will be in tension. The shear forces will be assumed positive if the force will try to rotate the side I'm taking in the clockwise direction. Let's go back. Ignore this half here. Let's say we're going to take this half. I need to add a shear force here. How can we make it in the positive direction? If we add this force, in a way, trying to rotate this member, this half we're taking, clockwise. Look at it, this force trying to rotate this member clockwise. That would be positive. All good? Now for the bending moment, how can we assume where is the positive direction for bending moment? Bending moment will be assumed positive if we create this smiley face, if you want to call it that way. This smiley face has an engineering name called sag curve. We always use that. The opposite of this is the hug curve. So this sag curvature always assume if the moment on this side of the beam and we're trying to bend this beam in a smiley face or a sag curvature, that will create a positive moment, or that will be our positive, assumed positive moment. So let's go back here. If I take this cut and I need to add these internal forces, the positive moment here will cause this piece to be bending in a sag curve or a smiley face. This moment here, assumed to be positive, or I need to draw an assumption for my bending moment yet until I calculate the actual value. The assumption will be that will try to bend this portion in a sag curvature. So as you can see, all of those are not important. Most of them are wrong anyway. I don't care. Those are reactions. I'm talking about just at these internal actions where I take the cuts. So if I have any beam here, guys, this is beam simply supported beam, A, B. And if I need to take a cut around C, that will produce the first portion. This is a pin support. That means I have axial reaction, horizontal reaction. This is RAX, RAY. That's the first portion, and that's AC. And that's the second half. I've got only vertical reaction here, RBY. And I've got C and B. Okay, one at a time, please. First of all, how can I assume we agreed on, I need to take either this half or that half, doesn't matter. Say let's to start with, we're going to take this half. Case one. For case number one, if the first thing we said, we have to draw the free body diagram and we have to show all the internal forces. What are the internal forces? How can I draw the internal forces here in the positive direction? We agreed to start with normal forces. How shall I draw the normal forces at point C, guys? Normal forces, that means axial forces. That means tension and compression only. Anyone? Yeah, going that way, Ina, thank you. So Ina is saying, I can say NC. What about the vertical force or the shear force? Remember, the rule was the shear force, we need
Going
to assume.
down?
Perfect, Hannah. Yep, that's correct. So the shear force will be assumed positive if we try to rotate this piece or the free body diagram clockwise. How can I rotate this AC clockwise? By adding a force down. Call it VC. Always the letter V refers to shear force. What about the bending moment? We agreed the bending moment will be positive if we make this portion smiley face. How would it go to make this smiley face? Clockwise or counterclockwise at point C?
So you mean the moment at point C?
Because we agreed, if I make the cut here, I have to add 3 components: horizontal force, vertical force, and bending moment. Always. For beams, I have to add 3 internal actions or forces. So I've added the shear force, I've added the axial force, I need to add the moments, which is unknown. All of these are unknowns yet. What is the positive direction for that?
Clockwise.
If I told, sorry?
Would be clockwise.
Clockwise, if we add a clockwise, look at it, guys. If we add a clockwise moment, that's how the curve of, is that smiley face to you? Look at it, the moment here is trying to rotate this member to do that curve. Is that a small face? Counterclockwise, okay?
Okay.
So if I go back here and make this moment that way, look at it, that will produce, let's call it MC, and that will produce this member if I rotate that moment there to that counterclockwise smiley face in this arrangement. Now, what about that arrangement here? If I need to add these forces here, let's just spread them away. This second half of the beam, anyone will be able to tell me the 3 different actions I need to add there in the positive direction? Without overthinking it, guys, just please remember all what we did for trusses. The first thing, without knowing what is right, what is wrong, we assumed I've got forces always in tension. That's what we assumed our positive sign convention. The same thing for beam. I don't know if the moment will be rotating this way or that way. I don't know yet. We will calculate this. But we have to all assume with the right, correct sign convention. And we all in beams have to follow the same sign convention. So the sign convention said, if I need to add normal forces or axial forces, they have to be always in tension. If I would add shear forces, add them in a way to rotate the portion of the beam clockwise. If you're adding moments in the positive way until you work out what is right and what is wrong, add the moment at the start to create a sag curvature, smiley face. So how can I add these forces here on this side now if I want to take this half of the beam? Because we agreed if I cut here, I can take this half or that half as a free body diagram.
Right. In C, we need a vertical force going down.
Going down, let's see. So, Fabio suggesting we got force here, VC. Okay?
No, wait. No, wait. We need to rotate.
Why shall I wait? Is that because your guy said that?
Now we need to rotate clockwise.
Perfect. Well done. So, I had the 2 options, guys. Very simple. Very simple. I had 2 options, either down or up. If I add this force down, look at it. It's rotating. It's trying to rotate this piece, BC, that way. So counterclockwise, that's incorrect. I have to add the force to rotate it that way, the shear force, positive. This means this is VC in this direction. Okay, and what about the axial forces? Is it going to be this way or that way? Where's Ina? Stella? Fabio? Everyone? Where is everyone? So a totally opposite direction where
Opposite
the other
to
side.
IC.
Okay, so it's all, I can say, always in tension. Correct? Always. The axial forces are the easiest. We can always say they're always in tension. At point C, in tension. What about the moments? How can we apply a moment to create smiley face on this piece of the beam?
Clockwise.
Clockwise, perfect. I can call it MC if you'd like. Okay, I don't need to make it that large, but I just want to show you this will create the beam, that will make the beam go that way. Okay, when you draw it, please don't draw it that large, or what you have to do, simple as that. Okay, that's it. That's the sign convention, guys. Now, first of all, any questions? When we do summation all internal forces, it makes 0. Yes, all internal forces, they should be equal and opposite to each other. Okay, correct. The point is, guys, I want to just highlight here, in almost everything, I don't say the majority, almost everything that we'll be doing, we'll be using this half. Why is that? Because in theory, we will agree to make sure that we're all following the same procedure. We will agree that we will be analyzing the beam from left to right. When I'm saying the word, I'm analyzing the beam from left to right. That means I'm always taking a section, for example, here, and looking at this part. And then another section here, and looking at this part. And then another section, taking this part, for example, okay? That's the, so we can make things simplified. It's an agreement for almost all engineers. We usually look at structures from left to right, okay? So if that's the case, that means most of the times we are following this rule. All the forces, V is facing up positive, N is not important anyway to us, which will be that way. But the most important thing for me, shear forces up will be positive, down will be negative. Moment rotating clockwise positive, counterclockwise negative. And let's leave it at that rather than complicating things. And as you've seen, when we take the examples, things will be clarified. But the understanding of the sign convention, please keep an eye on these 3 simple rules here. Axial forces should be always in tension. Shear forces should rotate the portion that you're looking at clockwise. Moments should always create a sag curve. Now, as we agreed, please, this has nothing to do with reaction forces. Look at these reaction forces here. They're not following any of these rules that we're talking about. Reaction forces are analyzed differently, right? At the start, when we start looking at the free body diagram, take a moment here, a moment there, and we get all these values for reaction forces. We are only talking about internal forces at the location of the cuts, of a truss, of a beam, doesn't matter, the structure, okay? So if we take this example here, and we follow the procedure, if I'm asking you the question, determine determine the normal force, shear force, and bending moment at point B. I need to know what are the values for shear forces, normal forces, and bending moment at point B. Why is that? You may ask. Why we're going through all this headache? Because think about it, guys. How can I design a beam without knowing how much internal forces or how much this beam is suffering, put it that way? How much is this beam trying to resist? How can I choose this beam should be this big or that big, steel or timber or concrete, wherever, if I don't know first how much problems I've got in this beam, how much moment, how much shear force, how much axial forces. I need to quantify those first. I know that's step one. I understand my problem. Step two, then I can start looking into the designing of the structural member that will resist these problems. I'll show you a quick example so you don't lose interest and you understand the reasoning behind this from an actual calculations that we usually do for structural design. Projects one. Okay, so in a particular structure, in any structure that I'm trying to work with, check if there's anything else here. That's layouts. No, don't worry about it. I'll see if I can bring up the actual layouts, the plans. Guys, if I'm just trying to do a structural design for a beam, okay? By doing this structural design there, the first thing I need to understand, first of all, how much this beam is supporting. So I understand where we're going with this down the track. How much is this beam supporting? How much supporting of live load, dead load, live load referring to the weight of people, weight of furniture, weight of, anything moving. We call it live load, okay? Dead load referring to all the fixed loads or weight of material, which is the weight of material, the weight of the flooring itself, the weight of the beam, walls, roof, all of these actual material are there and staying there for the life of for the design life of the project. And the wind load, regardless if we have wind or not, that's coming from the roof, the floor, and the walls above, for example. After I calculate all of this, we combine them, we create some safety factors into them. We will study all of this later on. But the point I get to these loads here, that's where we at, guys. That's where you guys are at now. If we are looking at a beam, simply supported beam, I've got a point load at the end, and I've got uniform distributed load on top of that. This rectangle here refers to uniform distributed load of 10 kilonewton per meter, and another point load at the end. The first thing we need to know, that's where we're at today. The first thing, that's deflection, we'll worry about it later on. But the first thing here we need to know, how much forces in this beam? Obviously, there's no axial forces. Can you see any axial forces here, tension or compression? There's none. All the forces are perpendicular to the beam. That means these are the shear forces. I need to understand how much shear force is in there and how much bending moment. And from this understanding, that's what we're learning today. This is called the shear force diagram and bending moment diagram. From the understanding of the shear force diagram, bending moment diagram, we can always say, I've got the maximum, I can look at it and quantify it. This is the maximum moment. This is the maximum shear in my beam. Then I have to go through the second process of doing the steel design, which is here, slightly different process, which is we're learning next year. These are the formulas that you'll be learning next year just for designing the steel members trial of 89 by 89 by 3.5 square hollow section. This is the properties. This is the calculation on it, and see, well, does it meet the applied axial force and bending moment? Is it adequate or not adequate? And then we agree, do we choose it or not to choose it, okay? So you can get your head around the overall process. This is where we are at today. We need to understand, in my being, so if you ask yourself, why did we do that for trusses? Why are we doing this for beams? We have to understand, first of all, how much the scale of our problem, how much bending moment, shear force I've got in that beam. The minute I establish that, then that's where I start looking at, okay, now I know my problem, I'll try to find a solution. I try to find the right size of steel or concrete or timber to solve that problem. We're clear on this, guys? So without doing this today, it's going to be a big problem for the future, guys. This is step number one for almost every single calculation you have to do in beams, mainly, okay? Shear force diagrams, bending moment diagrams are very important, please. Any questions so far before we take this example? Okay. So if I've got this beam here, and again, all I'm saying now, I don't want to know the entire bending moment diagram, shear force diagram. All I'm asking, give me the values of these forces at point B. That's where I'm interested, only, point B. So if I need to calculate that, what did we agree to do? The first thing, we draw the free body diagram. Yes? Can you guys please draw the free body diagram and find the reaction for this beam?
Yeah.
Thank you. I'm expecting, and please, guys, it's really important lecture. Please, everyone, hear me out. This is extremely important lecture for everyone, all of you guys. So please expect from me, I'll be calling you by name to give me the answers or values. Even if you raise your hand or you are ready to give the answer or not, I may ask, for example, now just without anything, I may ask for example, Severio, give me the answer. Although he didn't say I have the answer. Always ask you how to think through it. So everyone please work on your notebook. I don't want anyone to say I don't have the answer. Why? Because I didn't work on it. That's not acceptable today. I'm waiting for the reaction forces at A and D. If you find your answer, just keep it for yourself for a bit until everyone is done. Because at the end of this, I may ask Anna, because she joined late today. Are we, Anna? Can you please, when you're ready, add the reaction forces for point A and D? Actually, point A to start with. Bruno, got something to say?
Oh, sorry.
All good. Anna, if you let me know, just if you are with us, if you don't mind.
Hi, Aaron. Sorry,
Hi,
my
hi.
internet's not connecting very well today. Every time it just cut me. Sorry.
That's all good. Trust me, my internet yesterday was rubbish. So we are all guys going through the same thing. Okay, I understand. But would you be able to calculate the reactions for us? Shall I wait for you, or would you prefer if I ask someone else?
Yeah, I'll try to do. Sorry.
Okay, thank you. Okay, in case Anna joined us a bit late, I don't want to make pressure. Anna, I'll ask someone else. Anyone, please, can you type your reaction forces there for point A and point D? I'm just trying to emphasize, guys, any one of you, I may ask you today these questions. We're trying to emphasize, I can't see you face to face, unfortunately, to see the work that you guys doing, but it's really extremely important. The reaction forces are really good today. We are familiar with that and all the steps that we're learning today. Very important. You see today's lecture, very interesting, very easy. Just to give you a heads up, very easy lecture. And wait until the end, please, you will see. All we're asking, just I want you to work with me. So we've got the reactions at A and D are 4 and 2 kilonewton meters. Perfect. Now, if we make, and both of them are facing up, obviously. So if we draw the free body diagram, and we'll make the cut there. If I make the cut of this at point D, point B, that's what we agreed on. So let's say, copy this down. This is our cut. Okay, that's point B, where we need the. So I need to draw the internal forces and moment here. Okay, so if I need to draw the internal forces here for this half or that half. So I'll take another half there, Control C. Or that half there. These are the two halves that we've got. So let's focus on this right-hand corner half. Can you please draw the internal forces for me on that section there? We need to estimate our internal forces in the positive direction, as usual. I don't care what the reactions are. All I'm saying is I need to estimate my internal forces in the positive direction. So if you don't mind to turn your microphone on, if I need to draw the shear force, is it going to be facing up or down for this half? For BD. The estimated shear force to be positive, we agreed the rule for it, has to rotate this BD clockwise. How can I add a force here to rotate clockwise? For the shear force, is it facing up or down?
Facing up.
Perfect. And for the moment, to create a sag curve or smiley face on this portion here, shall I add it clockwise or counterclockwise?
Clockwise.
Perfect. Perfect. Okay. Now for this half here, internal forces always, normal forces always in tension. We're not worrying about that. Now for this half here, the same thing, moment would be positive if it was counterclockwise, because that's what create a sag for this half. Shear force would be positive to rotate this one, which is BA or AB clockwise. Shear force should be down, and normal forces should be in tension. Okay?
Aaron,
Yes.
I have a question. So the shear force shall always face in the way where we are trying to find the clockwise?
So shear force, you remember in trusses, we don't know, is it compression or tension, right?
Yep.
So the same thing for shear force, I don't know, is it up or down? Honestly, I don't know yet the value or the direction. I don't know the value and the direction. So we always agreed on this, first of all, estimate this in the positive direction. And the rule about the positive direction tells you that to be able to add the shear force in positive direction, that should rotate the portion or the segment of the beam clockwise. In this instance here, because I'm adding shear force on the right hand side, that means it should be down. In this instant here, shear force on left hand side, up. All good?
Okay, so always looking to move in the clockwise direction.
Exactly.
Okay.
Always trying to rotate this segment or that segment in the clockwise direction.
Okay,
Okay.
cool. Thank you.
No worries. So if we add those, this is for the smaller portion. Look at it, the moment will create a sag curvature. The shear force will create a rotation clockwise. Axial force is tension. So we always assume them in the positive direction, and then we will estimate that based on our calculations. If we get negative value, we change the direction. So if I have that as a free body diagram, look at it, very simple, very easy now.
Adam,
Yes.
Aaron, I've got a question.
Go ahead.
Why we have 5 kilonewtons going up at point A if we found
Because I think, yeah, there we go. So you guys made some mistakes there with your calculations. Let's go back. I didn't look at it. Okay, so let's look at that beam. That's why I'm saying, guys, very extremely important that we're doing. Thanks for noticing that. Extremely important, guys. Look, if you estimate your reaction forces in the wrong way, everything will be wrong. So let's take a moment around D for a starter. We've got sigma mg. This direction is positive, equals to 0. What do we have? 6 kilonewtons by 6. That's rotating counterclockwise, so negative. So I'm negative 6 by 6. Let me just move this up a bit so I can. Okay. And we have the reaction at A applied at 9 meters. We're assuming the reaction facing up. We're assuming the reaction facing up. So we've got clockwise, that's rotating, plus RAY multiplied by 9. And I do have a moment already there, which is rotating counterclockwise, negative. This moment is around D already, negative 9 equals to 0. So by doing this, we've got 6 at 6, we've got reaction at 9, that's negative, and that's positive. That will give us RAY equals to negative 36, negative 45 divided, sorry, negative 6 equals, take 9 again, equals 45 divided by 9, 5, and positive because I moved this one to the other side, that will be 5 kilonewton here. Did it make sense, guys? That's where the mistake you made, because you didn't take this moment, maybe. Therefore, if I take now the second formula, sigma Fy equals to 0, the easy one, I've got 6 down, 5 up. That means I should have another 1 kilonewton in there. All good? So that will give us our reaction forces, which is 5 and 1. Keep an eye on those, guys. You have lots of examples and the reaction calculations. Anyway, we will do a lot on this topic here. By the way, just before I forget, next week we have a quiz for method of sections for trusses. Now we made sure that we answer the questions, you guys understand everything. So your quiz next week would be method of joint, method of sections for trusses. That means reaction forces most likely will be calculated, okay? So please practice that. Okay. So by looking at the free body diagram of this part here, 5 kilonewton, I've assumed all of those positive direction. Now look at it, I've got 3 unknowns, the moment, the shear force, and the normal force. And I do have 3 equations to solve. Sigma Fx equals to 0 for this free body diagram. That means that will make straight away this force equals to 0. Sigma Fy equals to 0. That will give me straight away the value of the shear force, 5 kilonewton. Look at it, 5 up, this will be 5 down. We assumed it in the correct direction by coincidence. And sigma m equals to 0. You take moment at any location you would like, you should get equals to 0. If you want to calculate this first, you can take a moment here. So you can ignore all these forces. The shear force, the normal forces will be all ignored because they all come current to that point. And the only one force will apply is 5 multiplied by 3. That's going positive. If we're assuming clockwise positive, that should equal to this MB here. So MB should be 15. Right? These are the actual equations for that. Just very, very, very straightforward, easy equations. Not complicated at all, guys. Just taking a moment, sum of forces in the x direction, sum of forces in the y direction, and that should give you everything. Start always maybe with the vertical and horizontal forces, and then move on to the moment at the end, because that will give you more knowns and less unknowns. So in theory, guys, look at it. Exactly what we've done for trusses, method of sections. We take the cuts, show the internal forces, draw the free body diagram, use the equilibrium equations. All good? Now the good news for you, before we get to the good news, if I need now, based on that beam I showed you, remember that example I showed you? Well, the question is, how would I know? Just 1 second, please. if this is the beam I'm designing, guys, you are the engineer and you've got this job and you're trying to design this beam, how would you know where is the luckiest location on the beam that you take the section there, and that will give you the highest or most conservative situation or the most critical situation? How would you know? Who told you that B is the most critical value, critical point here? And maybe you could tell here that's where the point is applied and everything else is okay, which is not accurate, by the way. But if you may assume that, what about if we have a large beam with too many forces in many different directions? How would you know where is the luckiest spot to take that section that will calculate everything for you? So rather than doing that, what we have to do to come up with that argument for actual designing of the beam, to avoid that, we have to make as many sections as we can. We take if I have a beam like this with, I don't know, is it the worst case scenario here on the support or there, I wouldn't know. So what we have to do for this situation here, we have to take a section here to check this portion between A and B. I have to take another section maybe just here before the reaction, see how the shear forces are developing in the beam. Another section after the point B, another section here after and before that support. Look at it, how many equations, how many sections we have to take. And it's all the same, don't get me wrong. At the end of the day, it's all the same. It's not that very complicated calculation, easy. But look at how many equations you have to take or scenarios for just looking at one beam. And that's an easy one. Without uniform distributed load, without uniformly varying load, all of these cases. So therefore, we use a slightly different way in our work to estimate that. Rather than start thinking, that's the good news about this. Whatever we'll be learning here, I'm hoping all of this, first of all, are easy and simple for you, but I'm not going to push you now to master them and practice them too much, because rather than focusing at one section of the beam, based on the similar understanding, this is the important part for us to understand this correctly, we will use slightly different method, which is rather than finding one value of the shear force and bending moment at one location, we would draw a graph of the shear force. There's an easier graphical method to draw a graph of the shear force, how the shear force will change from this point, will go negative, stays negative, then go positive, then stays positive, then goes negative again, all the way to here. And similarly, we'll do another graph for bending moment diagram along the entire length of the beam. Think about it that way, as if I'm taking infinite sections around this beam. And that shows me every single millimeter of the beam, how much the shear force and bending moment. So that will give you the bigger picture of the beam. Okay? And that will be slightly different understanding. We'll discuss it today. And there's a slightly different methods for it, which is easier. And it's easy, put it that way. I won't say easier, it's easy method. Or what we're saying, just slightly different understanding. Okay? And that obviously will give us exactly the same values if we take these sections here. So if we took these sections, we get exactly the same values of what we're graphing here.
Can I ask something, Aaron?
Of course.
Maybe I missed it, but how do we decide the direction of the blue areas in the graph?
We will talk about this. We didn't talk about it yet.
Okay.
This would be part of our discussion on the second half of the lecture. Okay. So
right.
Everything above is positive, everything below is negative. Okay, we have an understanding. We will have an understanding of those. Anything above the axis is positive. Anything below the axis is negative. Depends on our value. You remember, based on our shear force data. Okay, we will talk about it when we come back. Put it that way, because I want you to think about it this way. When we start drawing these graphs, guys, imagine I'm taking section at every step I want. If I take a section here and I'm looking at this beam, that means I'm taking this half here. So if I take a section here and looking at all of this, I'm taking always the right-hand half. So we're going from left to right, correct? That's what we'll be assuming. We are going to start agree on always analyzing our beam from left to right. This means we are always dealing with this situation. That's what I've said in here, if you remember. We are always going to focus on this situation. The beam on my right-hand side, and I'm always taking a section here on the left-hand side, starting from left to right. Therefore, the shear force, if it's facing up, is positive. Okay, so that means, to answer you, Saverio, all these shear forces are up, positive. Okay?
Yes.
We'll talk about it anyway when we come back. Let me check. Yep, okay. Let's have a break, lunch break, guys. 12:30, 1 o'clock, we'll be back. And 1:05, please. Let's all be back here so we can make actual start on our today's lecture. All good? I'll stop recording so we can keep these recordings separate. All right, thank you guys. I'll see you after the break.